All right, so at this point, we have our equation of motion, or our treasure map for finding our final solution, and we have different tools that will help us make use of that map for finding our solution. However, it's a little convoluted, it's a little confusing, so we want to take these physics tools and sort of use them to translate the map into a form that's more easy to read, more easy to interpret, and then use that for getting the result we want, that temperature distribution within our heatsink, okay? What we're gonna do now is a very important moment where we take everything we invested in the last video in deriving the non-dimensional Biot number, and we use that to greatly simplify this equation of motion at hand, all right? So let's do that. How are we gonna do that? How are we gonna do that? Well, as the Biot number implies, it's a comparison between conductive heat transfer and convective heat transfer. So we're going to use one of the boundary conditions to try to pull out that parameter. And then since we know, in the last video, we did this analysis. If you haven't checked it out, check it out at the top right over here. Or maybe it's actually over here. Check out that video. We showed that Biot number for this particular heat sink using the same materials and using the data sheets that are provided from some of the engineers. It ends up being very, very small, which validates this approach, okay? It means that the Biot number is very small. So, in order to do this, in order to make that number pop out, we're going to make use of boundary condition number 1. And throughout this analysis, in order to ensure that the physics are acting properly, we will have to use each of these boundary conditions, all 4 of them, at least once. That's a common metric in physics. When you have your boundary conditions, you have to use every single one to get a valid solution, right? It has to behave as nature dictates, right? Okay, so first and foremost, taking this guy, and we can note that the temperature in this guy spreads out in the solid material, or in other words, the Biot number is very, very small, right? Due to the copper material, which is highly conductive, it's going to spread out. We can make use of boundary condition 1 to simplify our equation of motion. So boundary condition 1 states that the derivative with respect to x at x equals w, basically up here, is equal to the following. If we take that, pop it down here, what we can do is we can approximate this guy. So from here to here, we're going to approximate the derivative of the temperature distribution with respect to x as follows. We're going to say, okay, if we're moving in the x direction, let's take the temperature here minus the temperature here divided by the x distance. TWY up here minus T0Y down there. We traverse a distance x, or rather w, in the x direction, and this can be used to approximate the temperature distribution. Given the fact that our fins are very thin, very small, it makes sense to approximate it as such. If they were very thick, this would start to lose value. The derivative would not be as valid as described as such. But this particular approach where you approximate it as such, especially in engineering, is done quite often because, we get algebraic terms here. It's much easier to work with. You can get better results and you can get what you're trying to do. You can get to that end goal much more efficiently. Okay, so when you approximate it as such, the right side stays the same. And what we could do is we could take this guy here, the surface temperature minus the ambient temperature, pull it over here, and what we end up with, if we multiply W over here, we end up with the quantity HW over K. Okay, HW over K. What is that? Well, what we derived in the last video was that the Biot number is equal to H times some length delta L over K. This looks very similar to that. So what did we do? We just derived the Biot number. And this makes sense from a physical standpoint because if we look at the quantity on the left, what we have here is the temperature difference from the surface to the center. That's where the heat transfer and conduction is taking place, as we just showed, right? The temperature in the middle is going to be the max, so it's going to flow out towards the sides. That divided by the temperature differential from this guy out to the ambient temperature. That's sort of comparing conductive heat transfer to convective heat transfer, which in essence is the definition of the Biot number. That's what we defined it as in the previous video. And it's a comparison between those two mechanisms, those two processes of heat transfer, okay? So as we showed in the previous video, the Biot number is approximately 0 due to the parameters and the situations at hand. We took a look at the solid material, the copper material, the conductivity. We used the heat transfer coefficient for this flow of air, this kind of situation. And we used the approximate thickness of the fin. We found that the Biot number is very, very small. And this means, what does this mean? If this guy is equal to 0, right, that means, I'm going to do some work here. We can cross this guy out in essence. And then you have something sort of like TWY minus T0Y is equal to 0. And then TWY is equal to T0Y. What does that mean? That means that the temperature distribution from this surface down to x equals 0 in the center, there is no temperature differential. It's very minimal, very, very small, okay? And that's due to the fact that our conductivity is high and our thickness is very low. So it can spread out very quickly in that fin in the x direction, okay? So it's driven by the geometry and the material properties. And as a result of that, it means that the temperature distribution does not depend upon x. In essence, we could drop this guy out here, which is going to allow us to get rid of that guy shortly. And we can approximate Txy as approximately Ty. Now that's a big assertion, right? In the first video, what I said is, we're deriving the Biot number because it pops up multiple times in heat transfer analyses. And if we can show that it's very small, that can allow us to kick out a variable, eliminate it from our analysis, make our life easier, make it more efficient, okay? So that's what we did right here. Big assertion, big conclusion, super amazing for this analysis, okay? So we got that result there. However, what we still need to do is we still need to translate this into our map, okay? Right? We're taking this tool, our boundary conditions, and using it to translate this treasure map such that we can interpret it easier and get to our solution more efficiently, right? This has all the information we need to get to that end result. So we still need to try and incorporate this into this guy. And the way in which that is done is we can't just say that Txy is Ty, okay? That's not going to work, okay? Instead, what we need to do is, we know that this is going to be a constant temperature, but we don't know what that is. It would make sense to say that if you average over this distance, that's going to be the temperature in the x direction. So along y, we're going to have different parameters that are averaged, little slices into this fin. That's what we need to do. That's how we're going to transform this situation at hand, and that is accomplished as follows. We basically take an average of the temperature distribution over x, okay? To do that, what we're doing, or I guess I'll back up. We can sort of use an analogy of test averages. What is a test average? You know, you get a test back, you tell you an average. You take the sum of the number of tests. So each test, it's going to be 1 for each score. So let's say Billy gets a 90, Sandy gets a 92, and somebody else gets a 93. You're going to take 92 plus 90 plus 93, and then you're going to divide by the number of tests. In essence, this is what we're doing. So if we take this guy here, what we're using is the number of tests to average out the score. So we're doing the same thing here, where we're taking the geometry distance to average out the temperature distance. So this guy, this integral, right? An integral is analogous to a sum, where it's summing up small, infinitesimally small parts to get to the whole from 0 to w. In this case, we're going along the distance. So we're summing up this temperature along that distance, and then we divide by the entire x distance, and that gives us the expectation value of temperature in one slice of this fin, right? So we're averaging it in the x direction. This guy is very important. It crops up multiple times in heat transfer analyses, heat sink analyses, so on and so forth. This is known throughout the literature as the fin approximation. We're approximating the temperature in the fins by just averaging it over the distance, okay? So if we take this, our t in this guy is going to turn it into the following. However, we're going to need to apply this approach to each term, not only in the differential equation, our equation of motion, but we'll also have to do it for the remaining boundary conditions, which means this guy, number 2, 4, and 3. Okay, so that's what we're going to do next. Stay tuned. All right, to finish out translating this equation of motion and making it a bit easier to work with, we're going to have to average each term within it individually using the formula I just derived. I'm going to do that live with you and walk you through it. Okay, so the first term we're going to consider in the differential equation is the x term right here. So what we're going to do is we're going to use the same exact formula. We're going to basically put 1 over w times the integral from 0 to w of the second derivative of the temperature distribution with respect to x. And when we do this, this guy's a function of x, so we have to account for this guy. We drop from the second derivative down to the first derivative, and we end up with 1 over w dt dx, and that is defined from w to 0, from 0 to w. And what happens is when we take this guy, 1 over w times dt dx, defined at x equal w, minus dt dx, defined at x equals 0, we find something interesting. If we look at these guys and compare it to our boundary conditions, what we find is that this guy right here is actually just right above it. It's this guy, right? It's the derivative at x equals 0, which equals 0. So this guy vanishes. And this is this guy, dt dx at x equal w. So we can pull this guy in, and we end up with the following result. So this is equal to negative h over wk. That is times t w sub y, and I'm just reading off the boundary condition we derived earlier. That guy minus t infinity. And we can make one more simplifying assumption here. All right. So this, what can we say about this? Right? We don't want, if we have this guy, we want it in terms of the average parameter t average sub y. But we know that because the Biot number is very small, what we found earlier is that tw is equal to t0 when x equals w or x equals 0. They're essentially equivalent. So what we could do is we could say, okay, well, this is just, in essence, it's the average value. The average value at y, because there's no difference in essence. They're essentially the same. tw equals t at x equal w is equal t at x equals 0, right? There's no difference. So we substitute that guy in, and we end up with the following. So we get this guy, and we could say, basically get this, the x squared. We end up with the following. Okay, so we have this transformed quantity right here that we can pop into the differential equation, and it's all gravy. The next thing we need to do is do the same exact operation but for the other term right there. So let's work through that and figure out what we end up with. This one, fortunately, is a little bit easier. So we take 1 over w times the integral from 0 to w, and we have the second derivative with respect to y. All right, and that is over x. And what we can find is that since this is dependent upon y, we know that doesn't have any x dependence on it. We can, in essence, pull out the derivative from the integral. And what we end up with is 1 over w times the derivative of the following. I'm just going to check my notes really fast. Yep, that's exactly what I did. All right, and the constant you can pull in or out, that doesn't really matter. Actually, you know what? I want to leave it inside, so I'm going to pull this all the way out here. Pull in that 1 over w, and you leave the integral, which is dependent upon x, so we can switch as we want the operations. And this guy is txy. This is over x. What we find is that this is no different than the averaging parameter we derived earlier, right? So this is super easy. What we end up with is, literally, we end up with the second derivative of the average quantity of y. That's what this guy is. Remember, that's the definition we came up with. And that is over y. Okay? So, I guess I'm going to back up a bit. I messed up a little bit. Technically, I'm saying this is equivalent to that, but we need to put in this right here. All right? Just carry straight down. Okay? So this guy is equal to that. And what we want to do is we want to plot both of them into that equation. So in essence, what we're doing is we're taking this guy, which was the second derivative of t with respect to x squared, or the second derivative with respect to x, plus the second derivative of t with respect to y. All right? That is equal to 0. We're taking this whole thing and multiplying both sides by 1 over w, and we're taking the integral 0 to w along x. That's in essence what we're doing. And when we do that, well, we already solved this. We got this guy. So this gets plopped to there, and that gets plopped to there. And if I move the eraser out of the way, a little arrow, what we end up with, we substitute that into here. We get negative h over wk. This guy in terms of y minus t infinity. We get that guy plus basically this guy right there. Gets thrown right in. So we get the second derivative of the average t over y equals 0. So what we can do is just plop that guy over, just bring that guy over, and we get a much nicer equation. Look what we get. All right, so now we get the second derivative of the temperature distribution, the average temperature distribution with y. That is equal to h over wk t y minus t infinity. All right, so what did we gain here? What did we get? Okay, so we transformed the equation of motion. We translated our treasure map, so it makes more sense. And we find that it's only in terms of one variable, one independent variable, as opposed to two here. So you look at this. In order to solve this, you'd have to use like Fourier series solutions, I believe. Just going off the top of my head. This looks like an ordinary differential equation. Right? You could plop this guy over here, and then bam, you take two integrals, and you're pretty much good. So this is a language we understand. This is the mathematics of ordinary differential equations, which we know how to speak, right? We're trained in that. We're well-versed in that. So our tools allowed us to translate the treasure map, which has all the information for getting the end result we want, into something we can actually use, something we understand. Okay, so that's awesome. That's a great simplification. So what I'm going to do is I'm going to try and record this result right up here. And the remaining thing we have to do is just translate the boundary conditions, the ones we haven't used yet. Remember, we have to use each of them once. Use one of them for the Biot number and also for this transformation, which is good. So what we end up with is the second partial of the average temperature with respect to y is equal to, and nope, I did not miss a negative sign, h over wk times the average temperature in y, function of y, minus the ambient temperature T infinity. That is our new treasure map. That is what is going to get us to frickin' Willy Wonka. It's our golden ticket to the chocolate factory. Bam. That's our guy. Okay? So we got that. That can guide us to the end result. Next, what we need to do is erase all this crap and then transform our boundary conditions so we can make use of the rest of them. Okay? So if we erase all this, we are going to take the stuff we have not used. I just used this in our derivation. We have also used number 1. So we have to transform 2 and 3, I believe. That is correct. So as you can imagine, this one, super straightforward. Let's do that. Okay, so we take t x naught is equal to t naught. What we're going to do is 1 over w, 0 to w. We're going to integrate over x. And what happens is, if we do that to both terms, we end up with this guy right here is just Ty at 0, y equals 0. The average temperature right along there, that little sliver. It's going to be the same along the x direction, so our average temperature at 0 is going to be T naught. Now, we are averaging this guy, but since it's the same, basically what happens is you get W T naught, right? That's a constant, over W. That cancels. You end up with the same result, okay? So that's a boundary condition we got. Super easy, straightforward. I didn't really have to do it, but I like you guys, so I wanted to work through it. Next one we need to work through is number 2. That's one we have not used. So we take dt dy x at y equal L. That is equal to negative h over k t x L minus t infinity. All right. So we take this guy again, same operation. We average every term by multiplying by 1 over w and integrating over w in the x direction. And what's nice is this is like that second derivative we had in terms of y, right? It's not dependent upon x. So you just literally, you maintain that derivative and it turns into the average. So what we end up with for the left side is the average temperature with respect to y. Derivative with respect to y. Actually, I did not get this correct. So it eliminates the x, but we want the derivative at y, at that L parameter, y equal L. So this, y is equal to L. So we get the following. A crappy L, I'm sorry about that. And that is equal to negative h over k. Again, this guy literally gets transformed to the average. That's our definition. Basically our definition here. Same exact dealio. And same with the T infinity. So this becomes the average at L minus T infinity. And bam, that's what we get. Okay? So what I'm going to do is, just to record this for the future, we want to take these guys and write them right up here. So this becomes literally the average temperature at y is equal to 0 is equal to T naught. And this guy was number 2. it's literally the average temperature. And Y is equal to L is equal to, we just change the variables here, is the average temperature at L minus T infinity. All right, so we gained a lot here by taking physics and the intuit we have about the situation. We were able to eliminate one of the variables, reduced it down to just an ordinary differential equation. In essence, that partial should technically go away because it only has one variable there. And we know how to actually solve it. This is speaking our language of ordinary differential equations. If you know me, what do I like to do once I solve something? I want to verify it. And to verify it, I usually solve the same thing in a alternate way. So to wrap up this video, what we're going to do is we're going to derive the same information we just did here in a very mathematical, forced, not really forced, but you had to work for it, a lot of work. Instead of doing that, I'm going to try and take more of a physicsy, physical approach. And we're going to find we get the same exact result, which strengthens our confidence and makes us feel like we're doing this in a way that makes sense and jives well with our intuition, which is super important for any kind of physics analysis. Stay tuned for that. All right, to wrap up this video, tie a nice bow on it and call it done, what we're going to do is just one last approach, an alternate approach to show that you can get the same result and verify what we have derived so far. What that is known as is an energy shell balance. Okay, so what we're going to do is we're going to say that alternatively, we could have considered the energy flow over a control volume and applied conservation of energy, classical physics ideas. And we're going to do this over an infinitesimal element over the fin. It's going to be over a distance y plus delta y. Okay? So we take this guy, we're going to cut it infinitesimally as such. It's going to be a width of y plus delta y. And we're going to do it from x equals 0 to x equals w. Because again, we have no heat transfer across that center line. That's what one of our boundary conditions was used to derive. Basically this guy right there. Okay? So if we do that, we end up with a block which is blown up right here. And that's a distance of delta y in the y direction. In the x direction is just the top half, the w here. And what we need to do is we need to take a look at the heat transfer that's coming in and the heat transfer that's coming out. If you have not done like thermodynamics kind of stuff, fluid mechanics kind of stuff, a control volume is exactly what the words imply, right? It's a volume that is controlled, that's fixed, that's not changing, okay? So this happens when you have the same volume of space and you may have something flowing in or flowing out. In this case, we have heat transfer that's flowing in and out, but the mass right here, this mass, this chunk, this geometry is constant. It's a controlled volume, okay? If this boundary was moving, it would no longer be a control volume, okay? So what we do is we say on each boundary, what is flowing in is what is flowing out. We cannot create or destroy energy, so what comes in must come out, in essence, right? Unless we have heat that's generated inside. That would be an additional term in our balance. Okay, so what we have is coming in from this side, the base temperature has heat flowing in. We're going to have conduction heat transfer in. We'll call it Q in. Now once it comes in, we're going to either leave. We're going to leave on this surface through convection, Q out 2. Or we're going to leave through here to flow over here to through conduction to other parts of the fin. So this guy, Q out 1, is going to be conduction, okay? On the bottom here, we know that the temperature gradient is 0. The temperature gradient drives heat transfer, so that's 0. We have no heat transfer down on this bottom through the center, so this is going to be nothing. So what we do is we sum the Q dots that are coming in, set them equal to the Q dots that are going out, and that, in essence, is an energy shell balance that we could have used for deriving the same equation right here. Instead of going through all that hard grueling math. But doing it in two ways allows us to confirm we did it correctly. So what's going in is Q in. What's going out is Q out 2, convection. Q out 1, conduction. Let's plop in these terms here. And to help you, I've put the conduction, Fourier's law, and convection, Newton's law of cooling, right up here as a guide, okay? So, Qn right here. That's coming in here. So Qn is, we use the conduction. That's going to be negative K. And we have to use the surface area. That's going to be W for X, and then Z, right? This plane that's area that's it's flowing through, it has an X dimension, and then it comes out of the board in delta Z. So we have negative K, W, delta Z. Okay? And then what it's flowing in the Y direction, so our derivative has to be dt dy, right? The gradient drives the heat transfer, so we get a dt dy for what flows in. Now Q out 1, that's also heat conduction because it's going through the metal. So we get the same thing. We get negative K. It's also the same area it's flowing through, W, delta Z. And it's also in the Y direction, dt dy. But let me back up. This gradient, dt dy, is at the left side for this guy. So we're going to put y, and this is going to be on the right side, which is going to be y plus delta y, right? The reason why I'm using y is because it could be at any infinitesimal slice along this fin. We go at y, the size of the element is delta y, infinitesimally small. So that's the equation we get right there. Just want to double check. Yep, that is correct. And then we have convection. So then we have H. So the area it flows through, in this case, it's going to be a different area. So it's going to be delta y along this surface, and also into the board or out to the board. That's delta z. So it's H, delta y, delta z. And then we take the surface temperature, which is going to be T at X is equal to W. We get T, W, sub y. It's infinitesimally small, so we don't have to worry about the y coordinate. And then we just subtract T infinity. We're using this guy right here. Newton's law of cooling, baby. All right, so we get that. I want to make one last note that if it's at W, we found that this is the same as the average along the X direction. It's not changing. So right away we could say, oh, this guy right here, we're going to raise this guy, and we get the average temperature as a function of y. And if I check my notes, that's exactly what I got. So now what we want to do is we look at this, and we see if we have something that's like y plus delta y, and then a y, that once you should be thinking about a derivative, right? If the change in this quantity, the derivative, if it's over, in this case it would have to be over y, right? We're going from y to delta y. If we divide by y over that, that would be another derivative, right? So we want to isolate these guys right here after we sort of cancel all these terms. So we can divide by k, w, and delta z. Boom, boom, delta z over kw. And if we move this guy over here, what we end up with is the partial of y at quantity y plus delta y minus the partial with respect to y at y is equal to h delta y over wk. Rearrange that guy right there times t y minus t infinity. All right, should start looking familiar right here. So what we're going to do is we're going to take this delta y, throw it over here, and we know that we took an infinitesimal element. So what we want to do is we want to say, okay, we blew it up a bit to do our analysis. let's shrink it down to a small entity, right? So we take the limit as delta y goes to 0 of all this crap. And when we do that, we look at this and we say this is the change in the derivative of t over delta y when delta y goes to 0. That's the definition of a derivative. Okay, so this guy, if I move my eraser out of the way, this guy literally just becomes dt the second derivative respect to y. All right, and that's equal to h over wk t y minus t infinity. And we can just make a substitution in right there, change the variable. So it matches that guy right there. And what do you find? The interesting result is the fact that this, well, guess what? It's the same exact result we obtained from averaging each parameter within the equation, doing that hardcore math, all that work we put in. We got the same exact result. So it's a little quicker. It's not as cumbersome. But what is important is when you do the analysis, you got to make sure you have all the energy terms that are going in, that are going out. You get the signs correct, which can be tricky using this guy right here. If you get all that correct, this could be potentially an easier way for simplifying equations, something you can use. It's called an energy shell balance. Pops up a lot in heat and mass transfer, and that's a useful tool you can put into your tool set. So what have we found? We found that we have confirmed that this is definitely our equation map, definitely the treasure map that's going to be used for finding the solution that we're interested in. We have these extra tools, these boundary conditions that are going to be used in conjunction with this guy to pull out the information we need. And we're pretty much ready to actually solve the equation, get what we want. So in the next video, what we're going to do is we're going to simplify this a bit further. We're going to non-dimensionalize the equation, which is something that is done quite often in heat and mass transfer. We're going to do that. We're going to find out the Biot number pops out. We're going to be super freaking happy because we worked so hard to pull that out. It's going to help us simplify stuff. And then we're going to solve it, and we're going to figure out what it looks like and see if it jives well for our intuition. I hope you enjoyed the video. If you liked it, make sure you subscribe, hit that like button, and I hope to see your comments down in the comment section below. Stay tuned for the next video.